All right, everyone. Thanks again, Cliff, for the invitation. And today, I'd like to talk to you a little bit about the Advanced Quantum Testbed, Superconducting testbed that we have at Lawrence Berkeley National Lab. First, a little bit about myself. I'm the head of measurement at the lab and a research scientist at Lawrence Berkeley National Lab. But before I get into the testbed itself, just want to show you an image here. This is an image of a superconducting processor, in fact, one of the ones that we have in our lab. And you can see the qubits right there. There's sort of the rectangular shaped boxes there. And alongside, there are a bunch of elements that we use to measure the qubits, to have them talk to each other, and also to be able to control them ourselves. This is a device that we designed ourselves, but it can be quite complex. This is an actual chip made of many, many types of atoms here. And we can dive even deeper into this, looking at, say, a cross-section of what one of these looks like, and do layers of characterization to understand all the different elements that go on at the nanoscopic levels with this device, including the most critical parts of the circuit right here, where you see that line there is a Josephson junction, the most important element for a superconducting qubit system. And given this layer of complexity, I just wanted to share a quote that maybe reads as a bit pessimistic from Rolf Landauer, who was a leading physicist at the time, reviewing in the early days some of these proposals for quantum computation. And this one is specifically about superconducting qubits. And I think, in retrospect, it does read pessimistically, but I think a lot of the points he's making here still apply. And what we want to try and do to make things work is to fix that last part there. And taking into account all the noises, errors, and unreliability that comes with manufacturing such a complex device is something that's important looking forward. With this in mind, here at Berkeley Lab, we are taking an approach to quantum computing that involves what we think is a broad approach that's still required for the state of devices that we have right now. This includes many different layers of accessibility, including low-level access to many parts of the full stack, transparency, so openness about what exactly is going on with our qubits, what the error rates are, and what these errors actually come from. And to work on some of the challenges that described in the first slide, we think we need to make partnerships within our lab ecosystem and also with the broader community that's working on these types of problems. And to be able to do this in a way that is a free exchange, something that we can contribute in a two-way channel so that we can not only give access to our devices, but also have users provide and contribute so that they can improve over time. This improvement can come by reaching in both ways all along the full stack, including co-design with algorithms and co-design with hardware. And with this in mind, the Department of Energy in 2018 funded two national labs, ourselves at Berkeley Lab and our sister testbed at Sandia National Lab, to create quantum computing testbeds that can tackle these goals, keeping these needs of the community in mind. So with this all in mind, I want to first show you what this testbed looks like. First, the most important part is our large and growing team. This team composed of many scientists, from junior scientists, the grad student and postdoc level all the way up to senior level scientist at both Lawrence Berkeley National Lab and UC Berkeley. And we have a diverse set of expertise and background that are involved in this, and we think that's necessary to really create such a testbed and run it moving forward. Backgrounds of the people here include all the way in accelerator technologies, where they have a lot of expertise in FPGAs that we use to control our devices, all the way to physicists that work on the qubits themselves, actually fabricating them, designing them, measuring them. Material scientists that can produce the excellent images that you saw before and do this careful analysis that's required. And computer scientists that work on algorithms, compilation, and the like. So just to give a brief testbed, a brief timeline of the first phase of the program. For the first 2 years of the program, we really worked on the hardware itself, deploying high-quality devices that people can use, as well as developing the infrastructure that we need to measure these devices and reiterate on them to improve them. After that, we wanted to dive deep into what's working with our devices. With this, we worked with many different partners to develop characterization tools for the devices and see what the actual quantum capabilities of them they were. And then start working on a few test cases, so applications that people might have in mind. And then from there, we really want to open things up. And through our user program, we expanded and invited proposals to operate on our device. And this naturally leads to co-design, where users come up with proposals, things they want to run. Perhaps they don't run as well, but working with us, we can improve that. And then also learning from that, we can improve our devices down the line. So what are the key pieces of the testbed itself? First and foremost, it's the unique quantum platform that we provide. So again, we are a superconducting circuit-based quantum computing testbed. And we provide access to the full stack that is required to operate a quantum computer. Our mode of operation is to engage in deep user collaboration. So we're not necessarily in the place where we just want to have people run circuits through a cloud interface on our device. We actually want to collaborate with them so we can do projects that require that in-depth understanding. We really want to broadly explore the technology. We're not committing to any sort of specific implementation of superconducting circuits, but looking at broad ways of trying to actually develop this hardware moving forward. And then importantly, we want to develop the quantum workforce, developing these future quantum experts that will be using and running and creating these devices. So getting into our devices themselves, here is sort of a breadth of the types of devices that we have, specifically the superconducting qubit chips. And with this, our philosophy was to look at sort of broad range before we think about scaling to a large number of qubits. And we generally found this trade-off, where on the left, we have highly coherent and hardware-efficient devices. Here, the devices have limited connectivity, limited controls coming in. It's sort of the minimum amount that we need to operate the device. But we're able to, by stripping this device down, they're able to achieve high coherence qubits. On the other end, we looked at also a highly configurable and highly connected device where all of the qubits were interconnected and operations could be done between any pair of them. Here, we needed a large amount of tunability in the system, which at the sacrifice of coherence, we were able to unlock the reconfigurability. By understanding the limitations across the spectrum, we are informed about what we want to do for devices going forward. I won't go through all of these devices, but I want to briefly flash at least one of them here, because I think it reflects some of the science that we've been able to learn in the testbed here. So this is Trailblazer, sort of our main device for the phase 1 of the testbed program. Consists of 8 fixed frequency qubits with fixed coupling between them. We've been able to achieve high coherence times for superconducting qubits, which for that matter is around 100 microseconds. We've been able to really show that it's a high performing device. It has high fidelity readout. And importantly here, you know that I state that we specifically have 3-state readout here. And I'll go into a little bit later here, is that the superconducting devices that we have here, I called them qubits before, and many people do, but they're really many-level quantum devices. At this stage of technology, I don't think it's clear that a qubit is really the thing you want as your base unit for a quantum computer, as you would a bit for a classical computer. You may actually want to take advantage of all the extra quantum research that you have there. And we've done this exactly, being able to perform quantum operations on Q-trits, quantum 3-level systems with high fidelity. And actually being able to do that on a multi-qubit, multi-Q-trit device. That is a reflection of what we've learned from diving deep into understanding what would otherwise be a simple processor. There's actually a lot that we can do with this device. We've been able to develop many different types of entangling gates, including the 2-qubit differential AC star gate with fidelities over 99%, as well as a very different type of gate using Heisenberg interactions, also with high fidelities. And then most notably here, we have a linearly connected system where each qubit is only connected to its 2 nearest neighbors in a ring geometry. But we've actually been able to realize non-trivial gates such as the 3-qubit I-Toffoli gate with high fidelity. And this gate is done in a single pulse step here. So this is a reflection of some of the research that we do on processors using the quantum testbed. And before I get into some of the application side of our research, one thing I really want to emphasize is that a quantum computer is not just the chips that I've been showing here. There really is a full stack. And many of the limitations that a quantum computer will have, and I will speak mostly for superconducting qubits, but I think this applies to all types of implementations, is that the other parts of the stack, the controls which are classical computing devices, can be a bottleneck moving forward as we scale up. And realizing this by actually engaging with industrial partners to use their control hardware, we also worked with our team at Berkeley Lab to develop the first published open source control solution for superconducting quantum computing. This FPGA framework can be applied to off-the-shelf hardware platforms. Here we're using specifically a few Xilinx devices. And I think this is a great place for open source. This is a place where we desperately need to reduce costs. And there are all kinds of new capabilities as quantum computers advance that we need from these control solutions. And our approach, I think, is a bit unique in that we invited our FPGA team into our lab to actually work on the experiments themselves. They are actively engaging in these experiments specifically, and that allows them to gain intuition for what's required to run these experiments. And with that, they've actually created a tutorial that I recommend everyone take a look at if you're interested in this, because they've gone through sort of the full range of capabilities that you can do with such a device. Now, looking at the scientific landscape, we generally, so this is sort of something that's sort of naturally developed as we started the testbed program. Through both our internal science and engagement with our users, we generally perform science experiments in 3 general categories. The first being QCVV, or quantum characterization, verification, validation. In particular here, I want to highlight the development and implementation of randomized compiling, a compiling method that takes into account how we characterize errors and actually applies that to compilation so that these characterization methods are actually reflect how algorithms perform. I've spoken before about the novel quantum controls that we've created. In this bit as well, we've worked with our team that works on compilation and software to develop several compilation techniques as well. And then finally, applications on quantum simulation, looking at nuclear physics, many-body physics that can take advantage of some of the unique capabilities that we've developed, as well as trying out some error mitigation techniques that people have come up along the way. Now, briefly, I just want to go through our user program, how this actually works. It is an open quantum resource in that it has no cost to teams that want to participate and collaborate with us. We're very flexible in the types of projects that we want. Anything along the full stack, there's capabilities that you want, we'll absolutely consider that. And we want this to be a place where we exchange best practices. Working with users, we found that in a certain user project, we can develop some type of technology or technique that can actually apply to a different user's project that they were not aware of. And then finally, we want this workforce developed where the students, the postdocs, the scientists on our side also work with scientists, engineers out there in the community to build that sort of network of quantum information researchers. The process for user projects begins with the letter of intent. It's a brief paragraph, a one-pager, essentially giving you a brief outline of what the type of project that you'd like to do. That goes through an internal screening, and if we think that's appropriate for us, or if we have more questions, we reach out for either a full proposal or a discussion. If you go to the full proposal stage, this is, again, a pretty light load, about 2 pages. Just getting a background of sort of the proposal that you would run, as well as some background on the researchers themselves. After this, we go through an extra review, that's both internal and external reviewers. And here we are evaluating the projects for scientific merit, but more importantly, sort of alignment with our general program goals and feasibility with the resources that we have. Because we want to find something that fits a good niche for us, not necessarily something that people can just run on IBM Q, for example. And through this whole process, it's an open process. So we really want to engage with the users. We want to understand, okay, if there's a part of our proposal that doesn't quite meet our needs or we don't quite understand, we will reach out and try and get an understanding of this, and maybe even help try and craft the proposal in a way that's appropriate for our program. And the project areas can span a broad variety. As for how the projects actually go, initially there's a set of meetings between the AQT team and the users. Of course, a lot of this started during the pandemic, so the first phase of our program was mostly virtual collaboration. In terms of a queue, that's based on the project itself. If the resources are available and the staff is there to run it, then we sort of make an internal orientation about what we can run at which period of time, and also the needs of the user as well. The execution, we want the users to be involved in that, so they're run in a close collaboration. In some cases, we actually have a Zoom call, and the users run the experiments with us. In other cases where the users prefer to be a little more hands-off, there's more of a back and forth. And then finally, we really want scientific outputs. So we want to be able to publish the work that we have here. We've, in our first phase, had user collaborations with many institutions, including national labs, highlighted in green here, startups and companies, in orange, and also universities, highlighted in blue here. We have no restrictions on who can apply, and we've even had some international collaborations as well. In terms of our next phase, we just started that this fiscal year, and what we want to do is we want to grow this user community as it develops over time. We would love to have users on site for periods of time, if that's something that can be worked out with them. And we also want to continue our development for our workforce here with expanded internships and research opportunities. And if you'd like to collaborate, please visit our website, aqt.lbl.gov. And if you go to the user program tab, you can see where you can read about the program and also submit. So thank you.
Well, thank you, Ravi. I think we're ready for our panel now, so thanks.